So we've already talked about the schedule, right? So we know when the exam is, everybody has a reserved time slot and all of that. The two things to add today are the details of the review sessions. Okay, so we are going to have one review session tonight, 7 to 9 p.m. in Engineering 101. All right, the second review session, the SI super session, is going to be tomorrow, and that's from 4:30 to 6:30 right across the hall in Woodsoe 007. Okay, so make sure to hit those if you can. We started last time talking about carboxylic acid, so we made kind of a jump from talking about benzene and aromatic compounds to talking about a new functional group. So we looked a little bit about the structure of carboxylic acids, we learned how to name carboxylic acids, and we looked a little bit at their reactivity. We looked at we reviewed methods to synthesize or prepare carboxylic acids, and then we just looked at some general reactivities, saying that carboxylic acids can obviously act as acids, but we also saw that they could act as bases, right? And we know which of the two oxygens they would protonate on if they act as a base. And the third role they can be is they can act as electrophiles. And we'll see mostly those reactions coming up. So acids and bases is more important right now. So what we're going to do today is we are going to talk more about the acidity of this OH bond. Okay, both in carboxylic acids and in phenols. All right, see how different substituents, different groups can affect the pKa of those acids. And then we're going to take that, we're going to look at some physical properties. One of the interesting properties of carboxylic acids or acidic compounds is that their solubility will change depending upon the pH, depending upon whether they're neutral or whether they're ionized. And that provides us with some practical, things that we can do, right? Purifications and things become easy if you can just change solubility based on pH. All right, so I'll show you some of that. All right, I don't have a clicker today, so do we have any questions before we start? Nope. Okay. All right, so let's just look at some common organic acids. All right, and let's start off by trying to rank these. So let's say that number 1 is going to be the most acidic. Or let's start on the least acidic side. We'll rank number 4 first. Okay, so which of these molecules is going to be the least acidic, meaning it's going to have the highest pKa value? Ethanol, right? So ethanol has the highest pKa. Okay, we'll talk about why in just a second. Okay, which do you think is next? Phenol. Phenol is actually next. And then we have 2 carboxylic acids, right? And we haven't really talked about why they might be different from one another. Let's just say right off the bat that this acetic acid would be 2, benzoic acid would be the most acidic here. Okay? So when we're looking and trying to rank acids, what do we usually look at? What do we consider? Right, the stability of the conjugate base. So let's just draw out the conjugate bases. Okay, so we have, this is called the phenoxide. And I'm not going to draw the protons in, I'm just going to draw the conjugate bases here. We have ethoxide. We have acetate. and this would be called a benzoate. Okay, so based upon our rankings, it says that ethoxide, right, the one right here is the least stable, right? So why is it the least stable? No resonance, right? Nothing else. The electrons are just localized onto that oxygen. Okay, so this is the least because there's no resonance. All right, so we know that both carboxylic acids can have resonance, right? So they can both share these electrons like this. Give us another resonance contributor like this versus this. What about phenoxide on the left? Is there resonance there? Yeah, so this oxygen here, right, has 3 pairs of non-bonding electrons, and they can donate electrons into the ring. Okay? And so we can draw a number of different resonance forms like this. So that would become a ketone. We'd move that pair of electrons there on the minus charge. Go like this. We could do it again. Moves these electrons over here. These electrons move to the end. You know, we're kind of doing the same kind of resonance that we did, you know, with anions, any kind of anions that can be delocalized around in the ring like this. So this would put it over here, right? And we could do it one more time. Okay, and it would put, here I'll go ahead and do it. These electrons could go here, these would go here. Minus. And then of course we could push them back up onto the oxygen. Okay, so look at all the resonance that phenoxide has. And the carboxylic acid really only has these 2 main resonance structures. So why are the carboxylate anions on the right more stable than phenoxide, even though phenoxide seems to have a lot more resonance? Yeah, exactly. So it has to do with where that charge is going. With the carboxylate anions, the charge is being shared by 2 electronegative atoms, so both oxygens, right? So it's spread over those 2 electronegative atoms. For phenoxide on the left, there's lots of resonance, but 3 of the resonance forms put the minus charge on carbon, which just isn't as stable. Okay, so it adds up to being a less stable conjugate base, even though it has more resonance because it doesn't have as good of places to put that minus charge. Okay? All right, so let's just write out the pKa's just so we know here. Okay, the pKa of, this is kind of always one that I remember, 4.8 for acetic acid. Okay, it goes down a little bit, 4.2 for benzoic acid, but not a huge amount. All right, pKa of a phenol is about 10, and for ethanol, about 16. So alcohols are pretty close to the pKa of water. So what about the difference in stability then between these two? Okay, why is benzoic acid, why is apparently benzoate more stable than acetate? They both have the same 2 resonance structures. Yeah?
Because the benzene ring will help pull electron density away, so you can stabilize that negative charge and share between the
Okay, so the suggestion is that that benzene ring will pull electron density away. Why will it do that?
Because the double bond resonating.
Well, yeah, so the double bonds can move around the ring. Oops, I didn't quite do that right. Like this, right? But does that in its own right help spread out the electrons or the charge? Yeah, not really, right? Overall, it seems like it maybe is more stable, but it's really a relative stability between the acid and the conjugate base, right? That makes for what the pKa is. Yeah?
Is it more of an inductive argument because all of the carbon atoms are sp2 hybridized, therefore electron deficient?
Yeah, I think that's the argument here that we can use, is because in benzoic acid, all of these carbons are sp2 hybridized. All right, and remember, by increasing the amount of S character in the orbitals there, that leads to that carbon becoming more electronegative. So an sp2 hybridized carbon is more electronegative than an sp3, right? And so over here, we have sp3 next to the carboxylate, and over here, we have sp2. All right, so if we compare those two, the sp2 is pulling electron density away from the carboxylate, but through an inductive effect. Okay, there's no real added resonance that can spread that charge out, but it's just like putting an electronegative group next to it. It's pulling some of the electron density away, stabilizes it a little bit, right? We don't see a huge change in the pKa, but it does have some effect. Okay? All right. So let's look at other ways we can stabilize carboxylates. A bunch of different carboxylic acids. I should have made those bigger. All right, and so notice they all have halogens attached. All right, and so these are kind of the classic situations for having the inductive effect. And so if we look at the examples up on the top, we notice that if we go from this one right here, this chloroacetic acid, to fluoroacetic acid, okay, we're increasing the electronegativity of this halogen. So it has a stronger inductive effect. Okay, so it's more inductive. It's pulling more electron density away in the conjugate base. All right, that's the one we want to really think about. All right, if we go from chloroacetic acid and we add more halogens, right, notice that the pKa goes down, 2.8, 1.3, 0.9. So this is just kind of a, maybe it's not linear, but it's kind of a additive inductive effect, right? The more, if we have the same electronegative group, the more of them we put on, the more the inductive effect. Okay? This is all, oh, it says it right at the top, inductive effect. Now the bottom one, what's the trend for the bottom three? Okay, we're going from 2.9 to 4.1 to 4.5. So the pKa is rising as we go to the left. Yeah?
The electronegative group is closer on the lower pKa ones.
Exactly. So on the right, where the lower pKa is, the electronegative group is closer, right? So as that electronegative group moves farther away, the inductive effect falls off, okay? It just can't pull the electron density through that many bonds, okay? So as we go this way, so the electronegative group is farther away. All right, and remember, on all of these, what we're really trying to stabilize is not the carboxylic acids, but their conjugate bases. Okay? All right, so let's look at some substituent effects on benzoic acid. And I kind of cheated compared to your slides. I split one slide into two. All right, so let's look at these effects. All right. First off, maybe notice that these are all pKa values, and they're not hugely different. Okay, there's about 1 pKa unit difference in all of those. All right, but so what's the trend here? Let's look at these substituents and think about what they could do to the electron density of the ring. Okay, we'll work through this and then you guys can chime in. So here's an ether, a methoxy group. So what do we think of that? We just have to think back to the effects on benzene reactivity, right? So what does a methoxy group do? Donate electrons or withdraw electrons? It's more of an electron donating group, right? So this is electron donating. All right? So that's the one with the highest pKa, right? It's the least acidic. What about the one with the lowest pKa? It has a nitro group here. So what does a nitro group do? It's electron withdrawing, right? All right, so let's just draw out, I'm going to draw out 2 of these conjugate bases. All right, let's do the paranitro as well. These are the extremes. And we talked a lot about how these types of groups can donate their electrons into the ring and give all this extra resonance, or withdraw electrons from the ring and looking at the added resonance. So can either of these groups attached to the benzene ring help share that minus charge on the carboxylate through resonance, let's say? No, because the only resonance for this carboxylate is just back and forth, not really back and forth, but spread between these 2 oxygens. Okay? So if this group is donating, it just makes the ring more electron rich, and so it's an inductive effect. Okay? It's trying to donate some electrons to that carboxylate, makes it less stable. If we have the nitro group, we know it's an electron withdrawing group, makes that ring electron poor, and again, there's just inductive effect. It's just going to pull electron density away from the carboxylate. So these are only inductive effects. Okay? But still, electron donating groups are going to make the conjugate base less stable. Electron withdrawing groups make it more stable. Right? But the differences just aren't huge. Okay? Let's look at phenols, substituted phenols. And what do you think about those pKa values? They're spread over a bigger range, right? Because they go all the way from 10.2 down to 7.2. So now there's a 3 pKa, unit difference. All right, so why is there more effect from these same substituents if they're attached to a phenol versus a carboxylic acid? Yeah, so now we can those groups can participate in the resonance. Okay, so let's draw out the conjugate bases. We'll do them over here. Okay, so here's the phenolate, this paramethoxy. And remember that we just drew this out a minute ago. The type of resonance is to donate electrons. I'm just going to do I'm going to jump past a couple of resonance forms and put the electrons all the way over here. So we don't have to draw out every one each time. Okay, and so in this resonance form, we have these electrons and the minus charge exactly at the position where this methoxy group is trying to donate its electrons. Okay? So we have an anion, we're donating electrons through it, to it, that's going to make it less stable. All right, if we look at the nitro group, okay, let's go to here. Draw out the Lewis structure of the nitro group. Okay, and then I'm going to do the same thing. I'm going to just push these electrons 2 different spots over. Just skipping one resonance structure. And this puts the electrons and the minus charge on the position right where the nitro group is attached. Okay, so what does that allow? Right, we can have even more resonance then. So these electrons can go towards the nitrogen oxygen double bond electrons can go up onto the oxygen, and we get an added resonance structure. Like this. Okay? So this added resonance structure makes the conjugate base for paranitrophenol be much more stable. Okay? And so it's quite a lot more acidic. What about when we have that nitro group in the meta position? We don't see as much effect. So why would that be? Right, because the negative charge, or those electrons, can't land right on the position of the nitro group. All right, so let's draw that out. Oops. Okay, here's the conjugate base. Here's the nitro. Oops, and okay, so we can draw one resonance. Let's just draw the first one here. Puts the electrons on the position ortho to the oxygen. So they're here. And if we do this again, the electrons go right past the position that has the nitro group attached. Right? They don't land right there. So there's no way for those electrons to be further delocalized out onto the nitro group. Like this. Okay, so in fact, when it's meta, the added stability of the conjugate base mostly is inductive, okay, because the resonance can't move the electrons all the way out onto the nitro group. But for para or ortho, we have added resonance. Okay, so that's what makes these conjugate bases more stable. So this has added resonance. Okay, makes that more stable. Over here, there's no added resonance. So the effect that we see is only inductive. Okay? So in general, the effects that we're looking at activating and deactivating groups. We already did this. I did it all on that slide. But if we look at this table, right, that we already talked about in the last chapter, when we have activating groups, right, these are all the groups above this line. We talked about how all of these are electron donating. Okay, and if we have electron donating, what does that do to the stability of the conjugate base? Conjugate base is an anion, right? We donate electrons to an anion, it destabilizes it. Right? And that makes the conjugate base less stable, makes the acid less acidic. Okay? At the other end, these are all electron withdrawing. Okay? And so these are going to stabilize the conjugate base. Okay, and so that makes the acid more acidic. All right, and these are all basically listed in order, right? It's not just two groups, right? As we go down, those groups become more electron withdrawing, and so if we had them on the ring, they would get stronger and stronger acids. All right, does everybody follow that? Okay, so I think, the acid and base effects that we were just looking at just fit right in with all of the activating and deactivating effects that we learned already. Okay? Questions? Thursdays, everybody's so quiet. All right, so let's look at some physical properties of carboxylic acids. All right, so let's think just a little bit about, we're not going to do this too much, but about boiling point. Boiling point. Let's see if we can rank these. Oops. So we're going to rank them from lowest boiling point to highest. Okay, which of these molecules is going to have the lowest boiling point? Butane, right? This is the lowest. What's going to be next? Butanol? We don't have a butanol. The alcohol? The aldehyde will come next. Okay? So this would be 2. Right? Because aldehydes, there's no OH, so it can have dipole-dipole interactions, but it can't have any hydrogen bonding. All right? So now what do you think between the alcohol and the carboxylic acid? The alcohol comes next. And then the carboxylic acid is the highest. Because the carboxylic acid has this carbonyl oxygen that can form hydrogen bonds. It has the OH that can form hydrogen bonds from the hydrogen or from the oxygen. But what carboxylic acids oftentimes do is what's shown down here on the bottom, is that they dimerize. So here's one, this is showing how it's oriented. So here's its OH on one carboxylic acid, hydrogen bonds to the carbonyl oxygen of the other carboxylic acid. And the OH of this one, hydrogen bonds to the carbonyl oxygen of that one. So they can line up like this. They hydrogen bond very strongly here. It's basically this 6-membered ring that they're forming. And so carboxylic acids, in their boiling point, oftentimes act almost like they're twice as big, right? Because there's 2 molecules that are held together very tightly. All right? So carboxylic acids have really quite high boiling points, and their melting points would just mirror this as well. All right? All right, the next thing, just CHEM this time, but is the spectroscopy. Okay? And I think we looked at IR of a carboxylic acid before. Remember that they have this very broad OH stretch. Okay? Because there's just a lot of different hydrogen bonding arrangements that end up essentially with a lot of different bond strengths. And so if we see this very wide OH along with this carbonyl stretch, these two together tell us it's a carboxylic acid. All right? If we look at the proton NMR, we see oftentimes a very broad signal that's far downfield at 10 to 12 parts per million. That's the OH on the carboxylic acid. All right, and then here we're just seeing this ethyl group, but the characteristic one here really is the CH2 that's next to the carbonyl, right? Next to a pi bond is about 2, just over 2. All right, in the C13, the thing that really stands out is at 180, this carbonyl carbon. Okay, so this is right there. Okay, so carboxylic acids are around 180. Esters that we looked at are in the 160s, and amides are usually in the 170s. And then ketones and aldehydes are 190 or above. Okay? All right, so we'll come back to this later, and we're going to have some more of this for the final, but I won't be sticking this on the exams in the meantime, but I'll give you a few problems in your homeworks and stuff. Okay, so now I think the more practical and interesting thing is how the solubility is affected by either chain length or, like I said before, by pH. All right, so here's some generalities. All carboxylic acids are soluble in organic solvents, like a diethyl ether. I don't know if they're all in hexane, but ethers for sure. Carboxylic acids with fewer than 5 carbons in them are water soluble. So we know that, acetic acid, in vinegar, it's dissolved, it's diluted in water, right? Because it's water soluble. Carboxylic acids with more than 5 carbons are water insoluble. Okay, so if the chain gets too long, then essentially the alkyl part of the molecule dominates the physical properties, all right? Now the next part is that when we have carboxylate salts, they are water soluble, right? Because if we have this O minus, this is now ionic, and so it's increased its polarity, it can dissolve in water. All right, so let's look at these two compounds down here. So we have benzoic acid and its conjugate base benzoate. And we can think about when they would be prevalent. So if we put this mixture, whatever it is, this equilibrium, into a solution, acidic solution with a low pH, which direction would this equilibrium lie towards? Yeah, if it's acidic, it's going to go towards the protonated compound. Okay, so we're going to see this one over here at low pH. I'm going to call this the acidic form. All right, if we raise the pH, we add some hydroxide. Hydroxide will react with the carboxylic acid and go to the right towards the conjugate base. So this is what we see at high pH. This is what we could call the basic form. All right. Notice that the acidic form is neutral, whereas the basic form is ionic. All right, so between these two, which one would be more water soluble? The basic form, right? So this is water soluble, and it's usually going to be organic insoluble. All right. If we look at the carboxylic acid form, the acidic form, it's neutral. So this is going to be water insoluble, but it's going to be organic soluble. All right, so the solubility changes between organic and water depending upon whether that carboxylic acid is protonated or deprotonated. Okay, so we just have to adjust the pH to change its solubility characteristics. All right, now there's an equation that will describe what the ratio of the acid to its conjugate base is at different pHs. Okay, it's actually called the Henderson-Hasselbalch. But every time I say that to myself, I always think of Henderson-Hasselbalch. And I always made a joke of this time. All right, so we're not going to do that. This is the real guys here. All right, so here's the equation. You should have learned this in Gen Chem, right? So we're not going to really do any calculations, but what we want to know is the trends. Okay? And so we can rearrange this equation. We could move pH over, subtract pH from both sides. We get pKa minus pH equals the log of the ratio of HA over A minus, and then we raise both sides to the base 10, right? So we get rid of the log. And so what we would get is 10 to the minus pKa, no, I don't want the minus there. 10 to the pKa minus the pH equals the ratio of HA over A minus. Okay, so what we want to do is look at how the ratio changes as the pH changes relative to the pKa. Okay, so remember the pKa is a constant for a given acid. Okay, so that doesn't change. But we can change the pH of the solution just by adding acid or base. All right, so let's say over here, let's say what happens if the pKa equals the pH. Okay, and we're going to look at this ratio. Okay, we look to the right equation. If the pKa equals the pH, then 10 to the pKa minus pH is 10 to the 0, which equals 1, right? So the ratio is 1, and so when the pH equals a pKa, we have an equal amount of acid and conjugate base, okay, in equilibrium. All right, what happens if the pKa is greater than the pH, or we can say it the other way around, the pH is less than the pKa. Okay, what's going to happen to this ratio? Right, so if pKa is greater, so we're going to have a 10 to a positive exponent, right, which means that the ratio is going to be greater than 1. So we have here, I'll put it down here, 10 to the, I'll just say 10 to the positive x. So we have a positive exponent, which means that this ratio is going to be greater than 1, which means that the equilibrium lies towards the acidic side. right? So that makes sense, right? So as the pH goes down, goes below the pKa, then the equilibrium shifts to the acid side, okay? And if we reverse that, if pKa is less than pH, okay, so the pH is getting higher, the pH is above the pKa, then we get a value of 10 to the minus x. We have a minus exponent, and so we get this ratio is less than 1, which means that we have more of the conjugate base, and so it lies toward the basic side, right? So the main thing is, when the pH equals the pKa, we have a 1-to-1 ratio. When the pH goes below the pKa, we shift to the acidic side. When the pH goes above the pKa, we shift to the basic side. Okay? So we can just manipulate which direction we're at. And this gives us the ability to do just based upon on solubility. All right? So let's imagine how we could separate these two compounds over here. So we have benzoic acid, and we have, it's called anisole, right? It comes from licorice. So what we would do, so if let's do just an equilibrium here, okay? And so if we go up to the top, we could add acid, right? That's the acidic form of benzoic acid. So we add acid, it goes up like that. If we add base, it's going to go down. It's going to form the carboxylate anion. And what's it going to do to anisole? Is there an acidic proton on anisole over there on the far right? No. So there's going to be no effect. Okay? So at the top up here, these are both neutral. And so are they going to dissolve more in water or in an organic solvent? These are going to be more organic soluble. All right, so that's at low pH. At high pH, notice that we have one ionic species and one neutral. Right? So the ionic one, the benzoate, is that going to dissolve in water or organic? This is going to go into water. And the neutral one stays in the organic, or goes in the organic. Okay? So we can see here that if we raise the pH when we have this mixture, we can separate the two based upon solubility. Right? So what kind of an apparatus do you think you could use to do this separation? A separatory funnel, right? So we could use our handy-dandy separatory funnel. I'll show you my artistic skills here. Okay, so there's the stopcock there. So we have two layers. All right, so we're going to have, let's say, we want it basic, right? So we're going to mix together, let's say we're going to use, let's just be generic. We'll say organic, but our organic is going to equal, we'll use diethyl ether. Okay, and our aqueous, we want it basic, so let's use 0.1 molar sodium hydroxide. Okay? So, we have two layers. Is the organic layer, is that going to be the upper layer or the bottom layer? The upper layer, right? Oil and water, oil is always on top. All right, so this is the ether up here. Organic. Down here we have 0.1 molar sodium hydroxide. Okay? So we put our compounds in there, we shake it up, right? We vent it, we got to turn it upside down, vent it, right? All this stuff. We let them separate, and what's going to be in the upper layer? The anisole, right? The neutral one. So we're going to have anisole up here. And where's the benzoic acid going to go? It's going to go into the bottom layer, right? So here, let's just draw an arrow. This is going to go in here because it's water soluble now. Okay, just by shaking it up in the separatory funnel, we're able to separate these two. We can drain, we can drain them off, collect them in separate flasks. And then how would we get the actual carboxylic acid back rather than the carboxylate anion? Right, we could just add some acid and reprotonate it. Okay? All right, so this is an easy way to separate acidic from neutral compounds. All right, I'm going to add one slide in here, and we're going to finish up with one quick thing, and then we just have a couple of things to finish tomorrow, and then we'll just do some review after. I really have this, but I want to do it because it just fits right in. Okay, so here's another acid. Okay, so this is the conjugate acid of aniline. Right? And so we could look at its equilibrium here. So here's aniline itself. But this is the acid. This is the basic form. All right, so which one of these species would we have at a low pH? Yeah, the acidic one, right? So this is what we have at low pH. This is our acidic form. The basic form we have at high pH. All right? So the acidic form, is that going to be more water soluble or organic soluble? Water soluble, right? Because it's ionic. And the basic form is neutral, so it's going to be organic soluble. All right? So we could use the same type of separation with, we could say separate aniline from, let's just use anisole again. Like these, we could separate these two using a similar type of strategy. All right? But to separate these two, would we want the pH high like we did on the last slide, or the pH low? We'd want to have a low pH, right? Because what we're trying to accomplish is to make one of the species ionic while keeping the other one neutral. All right? So all you have to do is figure out at which pH they're going to be ionic or neutral. Okay, separate at low pH. All right? Okay, I will see you guys in the morning.